Good morning. I'd like to talk about a summary of numerical integration in a way that's similar to everything that I've talked about in the face-to-face class. The problem is we want to calculate the integral from a to b of f of x with respect to x, whose definition is the limit of Riemann sum business. If f is continuous, and if we can find an antiderivative for it, we can do the antiderivative method to calculate the value of the integral. On the other hand, if I can't get an antiderivative, or maybe if there were a whole bunch of these integrals that I wanted to calculate, it would be better to have some sort of computer method to do it. Initially, we're going to integrate over the entire interval from a to b. Later on, we'll carve the interval up into a large number of smaller pieces and apply the ideas that we're about to explore on the individual pieces. Those will be called composite rules. The methods that we're going to look at to start with will be this. In the interval from a to b, select some numbers, x0 through xn. I'm going to find a polynomial p that interpolates the data at x0, x1, out to x3. That is to say, the polynomial evaluated at x number j is f at x number j. We already know how to form such polynomials, so we'll take that as a given. If you want to see the details, you can look at a video that I've made called The Error in the Interpolating Polynomial. The upshot of it is that the actual function value, f of x, is the value of the interpolating polynomial plus a term that obviously represents how different f of x and p of x are. In the just mentioned video, we convinced ourselves that the error is the n plus first derivative evaluated at alpha over n plus 1 factorial times the product of x minus all of the x values in my interpolating set. The alpha is somewhere in the range x0, x1, x2 up to xn, together with the particular x that we're talking about. Because of the integral of a sum rule from Calculus 1 then, this says that the actual integral that I'm interested in is exactly equal to this quantity plus that quantity. This quantity is going to be my approximation to the integral, and this quantity will be the error that I commit by approximating this integral with this one. The simplest of all possible approximation methods will be I approximate my function with a constant function. I'm going to approximate my function by its value at x equal a. I could think of this as being an interpolating polynomial of degree 0 that interpolates at exactly one spot, namely x equal a. This is going to be my approximation to the integral, and this will be the error term. This integral is easy to do because f of a is a constant. An antiderivative for f of a is just f of a times x, which then has to be evaluated between b and a. This integral is going to have a little bit more thought required. If we assume that f prime is continuous and observe that x minus a is always at least 0 on the interval from a to b, then this is a continuous function times a function which is integrable, can be integrated, and doesn't change sign on the interval. I can use the mean value theorem for integrals to simplify this expression. If you use the function value at the midpoint, m, then you can write this equation out, and this is true. This leads you to suspect that the integral will be the approximation plus a term that's very similar to what we had before. But something remarkable happens with the midpoint rule. So keep in mind, this is the approximation for the midpoint rule, and this is the generic error, and this is the actual value of the integral. Suppose that I toss in another data point. I'm going to interpolate not only at x equal m, but also at some other point of the interval, which I'll just refer to as z. I'll have my Newton interpolation table for x equal m and x equals z. I can write out the interpolating polynomial. The error term in the interpolating polynomial is now 1 over 2 factorial times some value of the second derivative times x minus m times x minus z. When I integrate this term, I'm just going to end up with f of m times the width of the interval. The integral of this term is the midpoint rule. The integral of this term will be how different my new and improved approximation, the one based on both m and z, differs from the midpoint rule. And this will be my error term. We put the z in the hopes of getting a more accurate method. We're going to be surprised by what happens here. Writing that out a little bit more clearly, the actual value of the integral is the midpoint approximation plus the correction that gives me my new and improved method with this is the error term. This integral, believe it or not, is 0. So this says in reality the integral is exactly equal to what comes out of the midpoint rule plus that, since the middle term is 0. There's another layer to this also. This is true no matter what z is. Let me rearrange this a little bit to show you just how strange this is. The actual value of the integral minus the midpoint approximation equals that. Here is the weirdness. Variable z does not show up here, and yet this thing that doesn't depend on variable z is equal to something that on the face of it does depend on z. The amount of wiggle room that you actually have is when you change the z around, the alpha can change. And what we've figured out is, in this extremely weird way, the influence of exactly what the alpha is linked to whatever the exact value of z is in such a way that, despite appearances, this integral doesn't actually depend on what the value of z is, because that quantity doesn't. This is what's the actual error in the midpoint rule, is the integral from a to b of 1/2 times a value of f double prime times x minus m times x minus z dx. The remarkable fact that this is actually independent of z is really going to help us out here in a minute. Since this doesn't depend on z, I could make the z fairly close to, but not exactly equal to, m. Then I could make it closer than that. Then I could make it even closer to m, and this would still give me the error. I could make the z so close to m that it's all but indistinguishable from m. I could take the limit as z approaches m and get the following result for the error in the midpoint rule. And now we're in business. We'll assume that f double prime is continuous. X minus m squared does not change sign on the interval from a to b, so finally I can use the mean value theorem for integrals to simplify this. So evaluating the integral, I find out that the actual error in the midpoint rule is 1 over 24 times a value of f double prime times b minus a to the third power. If you'll go back and look, the left-hand rule had b minus a squared. If b minus a is small, then this is going to be considerably better. Another commonly seen approximation is I'm going to form the straight line that passes through the endpoints on the graph of the function. This is called the trapezoid rule because the region under that straight line is a trapezoid. If I want to get my Newton coefficients, it's perfectly straightforward. The integral of that's easy to figure out since it is a constant. The integral of a constant times x minus a is easy to figure out, and this is going to represent the error. Doing this part is perfectly straightforward. I'm just going to write the answer down. As far as the error term goes, I'll just talk my way through this. I'll assume that the second derivative is continuous. The rest of it, x minus a times x minus b, within this interval, x minus a is always non-negative, while x minus b is always non-positive. This product, x minus a times x minus b, is non-positive. It's integrable, and it doesn't change sign on the interval from a to b. You can do an analysis very much like what we've done before, and you'll end up with a value of the second derivative divided by a constant times b minus a cubed, just as we did with the midpoint rule. I'll leave that as an exercise to the interested. If you have three equally spaced x values, a, b, and c, you can fit a quadratic through the 3 points that go with x equal a, b, and c. The Newton table is, as usual, the polynomial of degree 2 or less that interpolates the function on the interval from a to c is this polynomial. Omitting all the details, after you do the tedious integrals, it turns out that the integral from a to c of f of x dx is going to be approximated by delta x over 3 times a sum. I'll have the function value at one end, the function value at the other end, and 4 times the function value in the middle. This is called Simpson's rule. If you do as we did with the midpoint rule, put an additional point in and ask how does that change your approximation to the integral, just as with the midpoint rule, you find out that it doesn't. Meaning, the error for Simpson's rule is the same as the error term for a 4-point method, with the value of that error not really depending on the fourth point. You can do the same kind of calculation that we did for the midpoint rule, and you'll find out that the actual value of the integral is this quantity, which is Simpson's rule, minus 1 over 90 times a value of the fourth derivative of f times delta x to the fifth power, remembering that delta x is the spacing between any successive pairs of numbers in a, b, and c. In an upcoming video, we'll see how to do the composite version of these integration methods and look towards how you would write a program to do this. In the meantime, I hope everybody has a good day. I'll talk to you again soon.